In this lesson we will see some very important algorithm, which is the orthogonalization algorithm. This algorithm is the one that will allow us to solve all the algebra problems, and therefore, it has a very high value. This algorithm was developed by Francisco Joubert, and let's see how it works. We will also see that in 5 minutes we can learn the algorithm, because it is a very simple pivoting algorithm. To explain the algorithm, what we need is a set of vectors, to be introduced sequentially in the algorithm. To explain it, we consider this matrix, that we have here, and let's consider their row vectors, that is, we will introduce 4 vectors in the algorithm. The first row vector is 1 1 0 1. Next, we explain the algorithm. Let's see how we can work with it. First, we start with iteration 1, and we use a small box, where we put the vector a1, which is 1 1 0 1, but even though it is a row vector in the matrix, here we write it in column. Next, we start with a matrix of a dimension corresponding to that of the vector a1. As the vector has 4 components, it has to be a 4 by 4 matrix. Though not necessary, it is convenient to start with the identity matrix. Then we write there the vector a1, and the identity matrix. Once this is done, what we have to do is to calculate the scalar products of that vector a1, by each of the column vectors of this matrix. So it is, vector a1 by vector v1, vector a1 by vector v2, by v3, and v4, and the product results are written in the last row, that is, where you have the t, which refers to the scalar products that we obtain. I have to indicate that when the starting matrix is the identity matrix, we can avoid the calculation of scalar products, because they are simply the components of the vector. Since the a1 vector was 1 1 0 1, the scalar products are also 1 1 0 1. Once we have the scalar products, you have to choose a column to pivot, which has to satisfy 2 conditions, so that it can be used. The first condition is that it has not been used before for pivoting. For that, when we use a column matrix as pivot, we change its name V by W. The second condition is that the scalar product cannot be 0. If the scalar product is 0, automatically that column is discarded, and cannot be used as pivot. Therefore, the 2 conditions are, that there has not been used before for pivoting, and that the scalar product is not 0. In this case, we can choose v1, v2, and v4. I have to say that the algorithm output, except for secondary reasons, is practically independent, equivalent, on the chosen pivot column. So, in principle, it is the same to choose one or another. In this case, for simplicity, let's choose the first column, that it has a scalar product different from 0, and is a vector v, what means that it has not been used as a pivot. Then, once that pivot column has been chosen, we mark it with an asterisk, and we paint it in yellow color, so that we can see it. Next, what we have to do, is to transform that matrix of iteration 1, in another matrix. Let's see how it transforms. First, let's see how to transform the pivot column. The pivot column is divided by its pivot, which is the corresponding scalar product. Here, the pivot is v1 asterisk, and its pivot is 1, because its scalar product is 1. We have marked it in yellow. Therefore, if the vector 1 0 0 0 is divided by 1, it gives the same vector, which is what I put in the transformed matrix, in blue color. Also, it should be noted that we no longer call it v, but w, with which we are indicating that this vector has already been used to pivot. At the bottom, you can see that it is 1, divided by 1, that is in the first element it is 1 and is multiplied by the pivot vector, then, we get the vector 1 0 0 0, that is, the same vector. How are non-pivot columns transformed? The non-pivot columns transform in the following way. We consider the column vector itself and subtract it the pivot value times the transformed pivot column, that is, the one in blue color. So, column 2, which is vector v2, which is 0, 1, 0, 0, becomes the same vector, which we write there, in green color, on the bottom, minus your pivot, which is 1, by the transformed pivot column, which is the column in blue color, that we obtained before. If we subtract, because it is minus 1, to the column in green color, the transformed pivot column, in blue, we have the one in green, to the right, which is what we put in its place, and we keep v, because this column has not been used as pivot before. With the next column, the same thing is done, the transformed will be itself minus its scalar product, that is 0, by the transformed pivot. Notice that, since it is 0 times the transformed pivot column, we subtract 0, and then the vector remains the same. Then, any column, whose scalar product is 0, is copied, because it is that vector after subtracting a 0 vector. Then, in this case, the column v3, which is 0, 0, 1, 0, transforms into it, 0, 0, 1, 0, and keeps the v name, because we have not used it as a pivot. With the last column, the same is done and it becomes 0, 0, 0, 1, minus its scalar product, which is 1, by the transformed pivot column, in blue color. If we operate, you get the vector minus 1, 0, 0, 1, that is the one we place there. Well, that's it, this is the algorithm. No more is needed. Therefore, it is a very simple one. I said 5 minutes and we probably have not reached 5 minutes. However, we will continue pivoting with other vectors, so that we can fix a little more the main ideas, and understand it better. Next, we have the last iteration matrix and we introduce the second row vector of the matrix, that we have written in the first column, which is 0, 1, 0, 1, that is, vector A2, and we have used the matrix resulting from the previous iteration. We calculate the scalar products and we change v2 by w1, which is the one we have used as a pivot, and by others, v2, v3 and v4, which are the ones we have not used, and the scalar products are written there. We have already put the scalar products and we choose a pivot column with the condition that it has not been used as pivot. You can use neither the w1, nor the v3, because its scalar product is 0. Then we have two alternatives left, v2 and v4. We chose v2, we select it as a pivot, and we put it in yellow. Now let's transform that matrix of iteration 2, in its transformed matrix. How is the pivot transformed? Dividing by its pivot, that since it's 1, you have to divide by 1, then it's the same, minus 1, 1, 0, 0, and we put it in blue, which is the transformed pivot column. How are the other columns transformed? It should be noted that we have two columns, whose scalar product is 0, the w1 and v3, so they pass. As they are, we copy them and there they are. For the last one, its scalar product is 1, then it will be itself, minus 1, by the pivot transformed, and after operating we get what it is below v4, which is the vector 0, minus 1, 0, 1, and that's it. We choose the next vector, the A3, which is 0, 0, minus 1, 1, and we calculate the scalar products for all the columns. Now, we have two pivot invalid columns, the w1 and w2, but the others are valid, because their scalar products are different from 0. We choose the v3, we put an asterisk, to indicate that it is a pivot, and we put it in yellow color. How is the pivot column transformed? Dividing by its scalar product, which in this case is -1, then we change the sign. The blue vector, which is the yellow vector, changed sign. We have put W3, because we just pivot and you will not be able to pivot again with it. There are two columns that are the W1, and the W2, whose scalar product is 0. Those are copied. And the last column is itself minus its scalar product, which is 1, by the transformed pivot column, what gives us the vector 0 minus 1 1 1, which is what we have put there. Finally, we put the vector A4. And we calculate the scalar products. Here, you can only pivot with V4, because the others have already been used. Therefore, we choose it and the pivot column transforms dividing by its pivot value, that is, -1, that is, changing sign. The other columns are calculated as them, minus their scalar product, which in this case is -1, times the transformed pivot column, and give that W1. The W2 gives it minus its scalar product, which is 3, by the transformed pivot column, what gives us this other vector. The third is itself minus its scalar product -1, by the transformed pivot column, that gives us that vector. With this, we finish the algorithm. We'll see now what happens if, instead of using the starting unit matrix, we use another regular matrix. That is, we are going to consider the same matrix that we had before, and we're going to repeat everything. If we repeat everything, we get these tables. Notice that at iteration 1, we do not start from the identity matrix, because that matrix is not the identity matrix. We have introduced the first vector, we have calculated the scalar products, we have found two zeros, and we had to pivot with V3. Then, we have introduced the second vector, we have pivoted with the first column, and we have obtained the matrix that appears in the iteration 3. Finally, we have introduced the vector A3, we were able to pivot with V2, and we have obtained the matrix at iteration 4. At iteration 4 we introduce the last vector, the A4, and we pivoted again, with V4, and we have obtained the final matrix. This final matrix, which appears now, is not exactly the same as the previous one. It has the same columns, but in different order, that is, except for the order, it is exactly the same matrix. This is also surprising, since we can use as initial matrix in this algorithm, any regular matrix, and we get the same result, or an equivalent result. In this case, it is simply affected by some permutations, what is surprising and interesting. As a review, and giving it an aspect with more colorful, here you have an idea of how the algorithm works. We introduce a vector, scalar products are calculated, the pivot is chosen, which is in yellow, and then the yellow column, which is the pivot, is divided by its pivot, and we get the blue one. The others become themselves inus their scalar products, times the transformed pivot column. If any column has a scalar product 0, it is copied, so, there is no need to calculate anything. Now let's justify why the algorithm is how it is. This algorithm was designed to obtain the subspace orthogonal to a subspace generated by a unique vector A1, and its complementary subspace. So, let's see what the properties of the algorithm are. Here, in this transparency, you have the first property, which tells us that the scalar product of vector A1, by the transformed pivot column vector VP*, is the unit, that is, the transformed pivot column. When scalarly multiplied by the initial vector A1, you get a scalar product 1, that is, it is normalized. Let's demonstrate it. Suppose we call TP to the scalar product of vector A1 by the vector column VP, the vector that is going to be the pivot. So, if we call it that, what is the transformed pivot? The transformed pivot column, which we are going to denote as VP*, is the VP, divided by the pivot, that is, VP divided by TP. What is the value of the scalar product of A1 by VP*? What is written there? We replace V** by its value, which is VP divided by TP, and take it to the numerator, because it does not matter to put it up or down. And what is A1 by VP? We have it 2 lines back, it's TP. Then, as A1 by VP is TP, and it is divided by TP, we get the value 1. Then, it is shown that the scalar product of the vector A1, that we introduce into the algorithm, by its transformed pivot, it always gives 1. Let's see now the second interesting property, which is that the scalar product of vector A1, by any of the transformed non-pivot vectors is 0, that is, the vector A1, by the transformed columns of those that are not pivots will give us a 0 scalar product, that is, the transformed non-pivot vectors are perpendicular to the starting vector A1. Let's prove it, because it's very simple. First, let's denote th to the scalar product of vector A1 by the non-pivot vh, we call him th. How do you get the transformed non-pivot column? The transformed non-pivot column vh*, is equal to the initial one, that is vh, minus its scalar product, that is, th, times the transformed pivot, which is v*. Now, let's see how much it's worth the scalar product of vector A1, by vh*, the transformed vector. We write it there, A1 by vh transformed, and simply, vh transformed, is replaced by its value, what we have got up there, and that is vh, minus th, by vp*. We apply the distributive property to this operation, and we have considered what each thing is worth. What is A1 by vh? That's th. How much is A1 by v*? We have seen previously that vector A1 by the transformed pivot was 1, then as this is 1, it is also th, and th minus th is 0, then we have demonstrated that, with this algorithm, what is achieved is that the initial vector A1, by those who are not transformed pivot, give a null scalar product, then they are orthogonal. The practical consequence of this orthogonalization algorithm is that, by introducing a vector A1, it breaks down the initial matrix, that contains as columns the generators of a subspace or a vector space, in 2 parts, one that is the pivot, that gives us the complementary subspace, and other vectors, which are the non-pivot ones, that generate us its orthogonal subspace. In this particular case, you can see that the orthogonal subspace to that generated by A1, its orthogonal, the orthogonal of A1, is the subspace generated by that matrix, which are the 3 columns that we obtained in the algorithm, and that the complementary to the orthogonal of A1, indicated by a top bar, is the linear subspace generated by a vector, which is the pivot. Therefore, all is clarified. This algorithm is designed to obtain the complementary and the orthogonal subspaces. It could have been interpreted differently, but it would be a little poorer, although very interesting. We could have interpreted the algorithm in this way. This algorithm is such that, by using the inverse of a matrix B as the initial matrix, gives us the inverse of matrix B after replacing in B, the row with number the 1 of the pivot column, by the vector that you introduce. Therefore, it also helps us to update inverses. This is what we can do with the algorithm. So, if in this scheme, we consider an initial matrix B and the matrix that we initially put in, instead of unity, is its inverse, B-1, if in matrix B, we change the row S, by the vector A1, and we call that matrix B*. What we get after pivoting is the inverse of matrix B*. That is to say, what the algorithm allows us, is to update the inverse of a matrix when we change one of its rows by the vector A1 that we introduce in the algorithm.